Okay, so yesterday we did some more examples of vector component addition. So today is going to be kind of a lot of practicing and looking at different types of examples of vector component addition. I'm also going to go over with you a specific type of vector addition question, and that is what we call boat questions. Usually they involve a boat. Okay, so we'll be going over that type of question. It's just perpendicular vectors, but the context can be a bit confusing sometimes, so we'll be going over those. But I want to use question number 1 here from your worksheet booklet, just to kind of go over the different types of vector addition that we've gone over so far. Okay, so right now looking at 1A, I've got 2 displacement vectors. One is 3 meters south, one is 4 meters south. What kind of vectors are those? Some collinear, yes. Okay, collinear because they are on the same line. Okay, so if I was drawing the diagram of that one, okay, I would have like 3.0 meters and then 4.0 meters, and then obviously my overall displacement would be 7.0 meters south. Okay, those are obviously the easiest kind. Okay, for B, is B collinear as well? Where I have 3 meters south and 4 meters north. Yes, it is, because there's no change in direction, okay, other than along the same line, right? For this one, they're collinear because it goes 3.0 meters south and then 4.0 meters north. Now my displacement is 1 meter north, right? Still drawing the same way, okay? So the fundamentals, regardless of whether they're collinear, perpendicular, or randomly angled, I don't know what we really call the other ones, but okay, the kind we were working on yesterday, we still draw them tail to head. Okay? We draw them tail to head, and we look at what our final product is going to be here. All right, what about C? What kind of vectors are those? So I go 3 meters south. And then 4 meters east. Those 2 lines are what? No. They're lines. So they're not collinear. They are perpendicular. Okay? There's a 90-degree angle between them. Okay? So they are perpendicular. Okay? And I've drawn them tail to head, same as I would any other vector. Okay? But now, in order to get my resultant, okay, which in this case represents a displacement, I go from my starting position to my ending position. Okay, that's my resultant. In this case, like we said, it's a displacement vector. Okay, if these were 2 velocities, it would be average velocity. If these were 2 accelerations, it would be average acceleration. Okay, it doesn't matter. We do it the same regardless of what type of vector quantity it is. Right. So I would have a magnitude and a direction that I could calculate, okay, using Pythagorean Theorem and trigonometry. So if I wanted to calculate D for this one, okay, the magnitude of D would be 4 squared plus 3 squared, okay, which is what, 25? Yeah, okay, so square root of 25 is 5, so we got 5.0 meters, and then we would have to calculate this angle here, okay, so theta would be 10 to the minus 1 of the opposite side, 4, over the adjacent side, 3. So we got second tan, 4 divided by 3. And so we got 53 degrees as our vector. And which direction is that? Other way. Not south of east, but east of south, right? Remember, whatever direction that angle arc touches is the second one. It's being measured from that direction, so of that direction. So this is moving east of south. But we could also have 37 degrees south of east, were we to draw the triangle that way instead. Okay, so two possible answers for that. All right, is that ringing a bell? Okay, so those are kind of the more basic ones because they don't involve you having to find a whole bunch of x's and y's like the ones we were working on the other day. Okay, now those ones we were working on the other day are more like, well, none of them in this question. We don't have any randomly angled ones here. Okay, so what I would like you to try right now is G. It's kind of like the camper question we did where the person walked from their tent to the lake and it had 3 different vectors. Okay, it's kind of like that one. So give G a try. I'll give you a few minutes on that. You're not going to have to find like x's and y's and use a lot of trig. You have to use one trig function at the very end. Okay, so give that one a try, and then we'll go through it together here in a second. Okay, so just in walking around, it looks like everybody's got the diagram drawn pretty well here. Okay, so we've got 7 meters south as our first vector. And then we have 6 meters east. And then we have 8 meters north. Okay, that's roughly to scale. It's probably not great, but it'll do. Okay, where do I draw my resultant? Always from the beginning to the end. Doesn't matter what kind of vectors they are, that's where the resultant goes. It connects beginning to end. Okay? Alright, so there's my resultant's triangle. Alright, it'll have this x and this y, but I won't need trigonometry to get it. Okay, and obviously this will be my displacement. So my x is 6 meters. Right? Because the only time I go east or west in this question is with this 6 meter one. So I'm going to end up 6 meters east of where I started, and I'm going to end up 1 meter north of where I started, because I went 7 south and then 8 north. All right? Everybody okay with that? All right, so if I'm wanting to find D, okay, D is going to be 6 squared plus 1 squared. Okay, so 30, whatever the square root of 37 is. Alright, so we got 6.1 for our displacement there. 6.1 meters, and then I need the direction. Okay, for me that'll be 10 to the minus 1. Opposite side is 6. Adjacent side is 1. So that'll get me my vector. I don't know why I actually put in the 1. All right, 81 degrees. And that'll be 81 degrees east of north. So I could also have 9 degrees, well 9 point something degrees north of east. All right, everybody okay with that? So big things to remember here that apply to all types of vector addition. Okay, they got to be drawn tail to head. Scale is important. Okay, these are the little fundamental things that we have to do right for when we get to more complex questions. Okay, we got to be very careful of how we draw it, and our resultant, okay, which often is displacement, always goes from beginning to end. It connects the dots, so to speak, okay, from beginning to end, and gives us our change in position or average velocity or whatever it is we're calculating. All right, questions on that one? Okay, let's look at boat questions before we get any further. All right, so in a boat question, you will have a river, not a lake. Okay, because in a lake, you just go straight. In a river, you have current and paddling speed. So I'm going straight downstream or straight upstream, which would make collinear vectors, okay, I am going to have some angled kind of resultant as a result of what's going on with me rowing and the current flowing. Okay, so here's how this question works. Have you write this one down as a boat question example. Actually, rather than say being rowed, I'm going to say headed straight across a river. And is Okay, so this would kind of be like part A of this question. What is the resultant velocity of the boat? Right? So there's two things going on here. They're going on at exactly the same time. The boat is being rowed across the river. Does that mean it's going across the river? Like if I row, if I get in the sheet down here, okay, and I row, try and row straight across, do I end up going straight across? Nope. If I aim straight across, I end up downstream. The only way I end up straight across is if I row slightly into the current, right? So if I aim straight across, I end up downstream. That's what's going on here. I might be rowing due north, but I'm not going due north. The river is pushing me east at the same time that I row, all right? So what I would see going on here is this. I have the rowing speed of the boat. I have the current speed. And I have what the boat actually ends up doing, which is the green one. Okay? So if somebody had like a drone and it was flying over top of where I was doing this, they would see the green line. They would see me following the green line. But that green line is the product of me rowing and the river flowing. Okay? Both of those things are happening at the same time. I draw them like one happens after the other, okay? But their effect is cumulative. Okay? They go together to produce my result, which is my average velocity. Okay? Now, can I calculate that average velocity pretty easily? It's just perpendicular vectors, right? Like there's nothing really difficult about this. It's the context of the question that can make these questions confusing. All right, so if I want to find the average velocity, I need the hypotenuse and I need the angle. All right, so all I have to do is go average velocity equals the square root of 2.5 squared plus 3.5 squared. All right, so we're looking at 4.3 meters per second for my average velocity and, or resultant velocity, and my direction will be the inverse tan of the opposite side, 2.5, over the adjacent side, 3.5. All right, so it's going to be 36 degrees. East of north. All right, so my average velocity is 36 degrees east of north. Okay? Just about every boat question you would get is going to have some kind of thing like that they're going to ask as the part A. Okay? That part is not really challenging. The context doesn't make that part really confusing. This is the part that gets people confused. Okay? So the second part of this question would go something like this. Okay, so if the river is 100 meters wide, how far downstream will the boat be when it reaches the other side? Because obviously, I'm not going to end up straight across the river because the river current is pushing me downstream while I row. So they give me one other piece of information. The river is 100 meters wide. So how am I going to figure out how far downstream I go? Like, that's perpendicular to the 100 meters. How am I going to do this? Do I know how fast I'm going straight across the river? How fast am I going straight across the river? 3.5 meters per second. That's how fast I'm rowing across the river. If it's 100 meters across the river, can I figure out how long it takes me to go across the river? Can I use that? What will I use it for? This is the tricky part. Two things are happening at the same time. They happen for the same amount of time. Okay? As long as I'm going across the river, I'm also going down the river. So if I can calculate how long I go across the river for, that's also how long I go down the river for. And I know how fast I'm going down the river. So if I have the speed and the time, can I calculate the distance down the river? I can. Okay? So this is what I have to do. I have to use the distance and the velocity across the river to get the time it takes me to get across. Then I can use that time with my downstream speed to get how far downstream I will be when I get across. Okay? What we have to recognize here is that both things are happening at the same time. Okay? Everybody all right with that? So, time equals d over v. So that's going to be 100 meters divided by 3.5 meters per second. Okay, so it's going to take 28.57 seconds to get across the river. So now, what I'm going to do is say, all right, d equals v times t. And I'm going to use now the speed I'm going down the river at and the time it took me to get across to figure out how far downstream I end up going. Okay, so that'll be this number, the time, times 2.5. So I'm going to end up 71 meters downstream of the point I started. So nothing mathematically difficult here, but it's contextually difficult. Okay? That is, the nature of the question, the nature of the wording, they can sometimes be a bit confusing. And we have to understand that in a situation like this, both across and down occur together, okay, at the same time for the same amount of time. Because once I get to the other side of the river, I'm not going across or down anymore. My boat will smash into the shore and that's it, I'll stop. Okay, and I won't be going either direction. Now we know in reality, your boat hits the other shore and then the back end swings around and then the boat flips around and you continue going downstream unless you get out of the boat. Okay, but we're going to assume that you're a reasonably competent oarsman and can get out of the boat quickly and stop it from doing so or drop the anchor or something. All right. Everyone with me there? Okay, so I didn't use any of this green stuff to calculate that, did I? Okay, this is the other thing we have to realize. I can only use vector quantities together if they point the same direction. Okay? What I often have people do is they use this velocity here that they calculated to calculate how far downstream they would end up. They're not going downstream at 4.3 meters per second. The resultant is 4.3 meters per second, 36 degrees east of north. That's somewhat downstream and somewhat across. It is neither one either. Okay? So I can't use it with a vector quantity that doesn't point the same direction. Okay? So I can't use a distance that goes east with a velocity that goes north of east. They're not going the same direction. They can't go together. Follow me there? I can use the time, okay? I can use the time from the across with the down because time is scalar, and I know that these two things occur at the same time. That I have to get from the context of the question, okay? But they occur at the same time, right? So that's one type of boat question, okay? That's a rowing across boat question. Now I'm going to make a going across boat question, which is slightly different, okay? So this is a going across question. The way I tell the difference is by, again, the wording. In this one, it says they want to end up directly across. So they're not going to accept being downstream. Now they want to end up directly across the river when they get across the river. Only way to do that is to row slightly upstream, slightly into the current. So what the question is asking for is, what angle do you need to point the boat in order to end up going straight across if you can row at 4 meters per second? Okay? This is something that if you became a pilot would be something you would do all the time. You would have to calculate your heading as a factor of airspeed, that's how fast the plane can go, and wind speed. Okay? If you want to end up going from Okotoks to Edmonton in your plane, okay, but there's a wind blowing straight east okay, at 50 kilometers per hour, you don't head to Edmonton. You'll wind up in Vegreville, okay, which is way east, by the way, if you don't know what that is. Okay, it's way east of Edmonton. So, and that's not where you want to end up. So you have to point the plane slightly into the wind so that the addition of both the plane speed and the wind speed will result in you going north towards Edmonton instead. Okay, you would have to correct for that. Same if you were a cruise ship captain. Okay, you're navigating the ship and there's an ocean current or a wind. You have to point into the wind a little bit so that you end up going straight, or you'll be way off course.
Kind of doesn't relate to this, but remember when you were doing like the bullet, like when it went like really long?
Mm-hmm.
Anyway, and you said you had to calculate like the rotation of the Earth. But
Yes.
You have to do that too.
To an extent, yes. Because you would have a live compass, your heading would take into account that the Earth would be spinning and would be going with it, but yeah, a little bit. Yeah. Okay, it's a bit of a difference between a projectile and a powered flight. An airplane is a powered flight versus a projectile that's just falling. All right, so what we have here is our boat and our river. Okay, so here's our river. I want my resultant to be this. Right? That's what I want to have end up happening. That's what I want my resultant to be. What I know is that I can row the boat at 4 meters per second. So I've got the 4 meters per second and I've got the river current at 3.2. So I'm going to draw the river current here. Okay, 3.2 meters per second. And my rowing speed. Meters per second. So I now this time know the hypotenuse. My resultant is not the biggest side of the triangle. That's the first time that's happened to us. Every other time our resultant has been the hypotenuse of the triangle. Is it okay that it's not here? It is. Because this is what would happen in reality. If I row slightly into the current, I don't end up going 4 meters per second because now the current is working against me. It's going to slow me down a little bit and push me back towards straight across. So my resultant's actually going to be slower than I can row the boat. I'm going to row like crazy, okay? But I'm not going to go 4 meters per second because the current will slow me down and end up making me go straight across. So what the question is asking for is this angle. It doesn't even care how fast you're going across. It just wants to know what direction do you have to go in order to end up going straight across. All right? So what trig function am I going to use to get that?
Tan.
Nope.
Sine.
Sine. Inverse sine. Yeah, I'm going to use inverse sine. Why? I have the opposite side and the hypotenuse. Okay? I would love to use tan because it's my favorite, but I can't because I don't have the adjacent side to the angle, so I have to use sine instead. So I'm going to go sine to the -1 of the opposite side, 3.2, over the hypotenuse, 4.0, okay? And that will give me the heading that I'll have to use. So second sine, 3.2 over 4. Okay, so I have to head at 53 degrees into the current. Okay, 53 degrees into the current. So if this was, if it was straight north and straight east here, I would be going west of north in order to make this happen. Okay, so 53 degrees into the current or upstream, 53 degrees upstream, it would get me that end result of going straight across the river. Now 53 degrees is not what this triangle looks like. Okay, this is a terrible triangle in terms of scale. Okay, this would look more like this. Okay, I'd really be rowing upstream, okay, in order to end up going downstream because the current and my ability to row are not that different. Okay, they're very close in their magnitudes, okay, so it's almost like a 45. All right. Everyone okay with those two types of boat questions? So most of the time, it's a boat. Once in a while, it's a plane. Okay? If it's a plane, it's the plane and the wind. Right? If it's a boat, it's the boat and the river. but they're always the same kind of thing. All right. Any other questions on the boat question? All right, I would like you guys working on question number 3 for right now. The correct answers are here in bold, so you can check them as you go. I don't have the complementary angles on here, but obviously there would be a complementary angle to each one of these answers that would be correct as well. So for C and D, it would be 15 degrees, and for E, it would be 47, and for F, it would be 9 degrees. Okay, so give those ones a try. The first 2 are pretty easy. Okay? They're kind of collinear, but C and D are very much like what you would see on a unit exam. So if you're looking for what level of difficulty I'd ask on a unit exam, C and D would be more like that. All right. If you've got questions, guys, I'll come around, okay, and I can give you some help here. Okay, guys, I'm just going to quickly do the drawing here for C, just so you can kind of see what that diagram's going to look like. So in C, we go 8 meters east, and then 6 meters at 35 degrees north of east. So I'm going to draw a dotted line east to act as my reference. I'm going to go 35 degrees north of that for 6 meters. Okay, so now I've got the x and y components of that 6 meter triangle, and my resultant goes like this. Okay, I can draw the resultants triangle above and over if I want, but the most logical thing for me to do is to draw it right over top of this, because that really tells me, all right, if I want to get green x, it's 8 plus x, 8 plus red x, okay? And whatever red y is what green y is, right? They're the same. It really tells me that if I draw it that way, okay? Then I just need to get theta and my overall displacement. You could obviously still draw it up here if you wanted to. Okay? That's entirely up to you. Okay, so let's kind of walk through the rest of this one here. Okay, we're finding all our x's and all of our y's. Okay, the x for the black vector is 8.0 meters east, because it goes due east, which means the y component is 0, right, because it doesn't go north or south. Then we have our red vectors. Okay, red x is the adjacent side, so it'll be the cos of 35 times 6.0. Okay, so that's 4.91 meters east, and then the y component is the opposite side, so it'll be the sine of 35 times 6.0. Okay, 3.44 meters north. All right, so now that I have that, now I can calculate my resultant. That's the green triangle. The resultant x. Resultant x is going to be 8.0 meters plus red x, which was 4.91. All right, so 8 plus 4.91 is 12.91 meters east. And our y components are equal, we already said. So the y component for the green triangle is 3.44 meters north. Now that I have those, I can calculate my hypotenuse and my angle. Right? So then I have my Pythagorean theorem. Right, and that's going to come out to 13.4 meters. And then my angle here, 10 to the minus 1 of 3.44 divided by 12.91 is going to give me my 75, well actually 15 degrees north of east. Okay, but obviously 75 degrees east of north would be that angle, and that's equally correct. Right? Okay, how many people are on D? How many people are done D? Okay, I'll give you some more time before I draw the picture for D. Okay, I'm just going to quickly draw the diagram for D. Okay, we got 12 meters due south. And then our second line is 15 meters, 55 degrees east of north. Okay, so I'm drawing my reference line north. Okay, but I'm going to go 55 degrees. That's more than halfway down. All right, so it's going to look like this. It's probably not even quite right. Okay, on this one, scale is important. Okay. That feels a bit better. Okay, so I've drawn this line longer than the 12, slightly. Okay, I've made this angle fairly accurately representative of 55 degrees. It's more than halfway down. Okay, and I've drawn my triangle. So here's x, here's y. There's my angle, and my resultant goes from beginning to end. Like that. So that's what your diagram for D should look like. Okay, that one's tricky. Lots of people just draw it going straight back up, nice and level across. You're not that lucky. Okay, it's slightly below. Okay, and this is again where scale's really important. Okay, this line is only 3 meters longer than this one, and it's angled more than halfway down to the x-axis. So there's no way it gets even close to getting back up to the top here. Okay, so for D, right, we want to find our x and y components now at this point. Okay. For our first vector, okay, the black one, x is 0 meters. It doesn't go horizontally at all, so it has no x component. Okay, and the y component is 12.0 meters south because it goes due south. Right, so those two are pretty easy. Okay, then we've got to look for the x and y components of the red triangle. Okay, x is opposite to the 55 degree angle. So red x will be the sine of 55 degrees. times 15. Alright, so 12.29 meters, and that is east. Okay, and then our y component is adjacent to the 55-degree angle, so it'll be the cos of 55 times 15. Okay, so it's 8.60 meters north. All right, so now I want to find blue x and blue y. Right? Well, blue x is easy because blue x is what compared to red x? It's the same, right? It only goes east in one part of this trip. So blue x and red x are equal, right? So I don't even really have to do much thinking on that one. This one is 12.29 meters, okay? And it's east, right? Now the y component, that's a little bit trickier. I go 12 meters south, and then according to my calculations, I go back 8.60 meters north after that. So I still end up south of where I started, okay? But that means that calculating blue y will mean going 12 meters south minus the 8.6 meters that was back north, right? So we're going to give a 3.4, something like that. But we're actually going to punch that number into our calculator. Okay, so we're going to steal this number the first time I enter the 12. 12 minus that number. All right, so 3.396, okay, is our blue x meters south. All right, so now that I've got these two sides, okay, I can now calculate my overall displacement's magnitude using Pythagoras and this angle using tree. All right, so d will be the square root of 12.2 squared plus 3.4 squared. Okay, I'm actually going to use all the decimals in my calculator when I do that. Okay, I'm not going to shortcut. So that number squared plus that number squared. Okay, so my overall displacement's 12.75 meters. 8 meters. And then my angle, okay, to find theta, that'll be 10 to the minus 1 of, for me, opposite is the 3.4 divided by 12.29. Right, so I'll get my theta there. Again, using all the decimals in my calculator, not cheating. Okay, so opposite was that one divided by that one. All right, so we're looking at an angle there of 15.45 degrees. And that is south of east. Okay, in this question, I was given 2 significant digits everywhere, so my answer would only have 2 significant digits. So we're looking at 13 meters at 15 degrees south of east, or at 75 degrees east of south if you drew your triangle like that. Okay? All right with that? Those two are exactly like the exam questions I gave on vector addition in the last 2 semesters. Like literally the diagrams look just like that with slightly different numbers. Okay? So you know exactly what to expect, okay, in terms of that. Okay, how many people are done E and F? Okay. How many people are done E? All right, I'll give you a few more minutes and then I'll draw E up here. Okay, so if we're looking at the diagram for E here, okay, so we got 5 meters at 26 degrees south of east. Okay, so I'm going to go east, then I'm going to go 26 degrees south of that. Okay, and then my next line is 58 degrees west of north, which I really didn't position that very well to draw that part on here. Okay, so I'm just going to move it down. Right, so now I'm going to go west of north, and I'm going to go 7 meters, okay, at 58 degrees west of north. So this one's tricky. Why is it tricky? Because it overlaps a lot, okay? And so we got to kind of figure out where that other one's going to go. So I'm going to go and draw my line north. Okay? I know I'm going to go 58 degrees west of that. So that's more, okay, way more, okay, than this 26 is here. Okay, everybody follow me on that? Okay. So here's what I'm going to do. I'm going to just faintly draw that triangle, something like this, and say X and Y, and then I'm going to draw it up here. And what I'm going to do is I'm going to calculate what these two sides are, so I know exactly what to do for my diagram. Is it okay that I do that? Yeah, I mean, if I'm not sure and I want my diagram to be right, I can calculate these things before I draw the diagram. Then I'll know, okay, do I need to go further up than this one, okay, or not as far up than this one? So what I'm actually going to do is calculate my x's and y's and then figure that out, okay? So I'm going to calculate black x, okay? Black x is going to be the cos of, what angle is that? It's 26, right? Cos of 26 times 5. Right, so that one's 4.5. Red x, okay, is going to be the sine of 58 degrees times 7. Right? So all right, so it's 5.9. So I didn't do a bad job of estimating this. Okay, it does go past where I started here. Okay, so I didn't do a bad job estimating. I need to make it a little bit longer. Okay, so I put it out to there. Now I've got to figure out, do I go higher or lower than the other y? So I'm going to calculate the other y. Sine of 26 times 5. Okay, 2.19. And then I'm going to go cos of 58 to get the other side. 3.7. So actually, I did a decent job here. Okay, I did draw this pretty much accurately. This is 3.7. All right, so I'm just going to kind of keep my line the way I had it, kind of like that, except it should be straighter. Got a little crooked there. Okay, so that means then that my resultant goes here to there. It's a tricky one. Okay? It is really tricky because it almost completely backtracks. Just enough that it's not collinear. Just enough to mess with you when you have to draw a diagram. So one like that is a good one to use that separate triangle method on, which is effectively what I did. Okay? I calculated the x's and y's before I drew my final triangle, because really there was no way for me to know for sure drawing it tail to head. Okay? So in a question like that, the separate triangle method is not a bad method to use. Okay, so on this one, like I said, we've already kind of calculated all the x's and y's. We've got red x, red y, black x, and black y. Okay, so now if I want to get my resultant, okay, I can get green x. Okay, green x will be 5.9 minus the 4.5 here. Okay, because 5.9 is west and it's the bigger number, minus the 4.5. Okay, that was going east. Right, so we got, what was it, 1.4. Okay. No. Yes. Okay, meters. Is it meters or kilometers? It's meters. Okay. And that is going to be west. Okay. And my y component, okay, the first one goes south 2.19 meters, then I come back north 3.7 meters, so I'm just going to go 3.7 minus 2.19, right? And actually get my real numbers here. So we got 5.9 minus 5. Okay, so that got us the 1.4. Okay, and then I have to do the 3.7 minus 2. So we're looking at 1.51 there. And that is north. Okay, so now I've got my resultants triangle. So if I want to get D, okay, D will be the square root of 1.4 squared plus 1.51 squared, obviously using all the decimals in my calculator for that one. Okay, so second square root. Okay, so we're looking at 2.1 for our overall here, 2.1 meters. And then our angle, tan to the minus 1. The way I drew the triangle, it's going to be x over y, so that's going to be 1.4 divided by the 1.51. Okay, so we're looking at 43.5 degrees, which is going to round to 44 degrees. And that, for me, is going to be west of north. So you could also have 46 degrees north or west if you drew the triangle the other way. Right? That's about as tricky as they get in terms of overlap and having tricky diagrams and such. Calculations are always the same. Okay. Questions there? All right. How many people have done half? Okay, didn't think so. All right, keep going on F here for a couple more minutes. I'll draw the picture before class is out. Tomorrow's quiz, we'll have some vector addition stuff on it. I'll put it to 320 today. So for that one, I'd have my 9 meters, 35 degrees north of east. Okay, so I've got east. Okay, so I've got exactly what you have. Okay, and then my next one is south of east. So I draw my reference line east, and then I go 25 degrees south of that. Resultant looks like